Today we're talking about confidence intervals. This is a new chapter, chapter 6. So let's get started. We've got a population. We've done this before. You want to know something about this population, and it's too large to really survey everybody in the population. So you pull a sample, giving one of the techniques that we learned in chapter 1. And here's your sample. And let's say, for example, for our purposes in this section, let's say that we're interested in the mean of the population for measuring something. So if we want to know what the mean is, that's the question of that population. What we do is we take a sample and we find the mean of that sample. We'll call that X bar. So, and then we say, hey, that's a pretty close estimate of what that population is. Now, what we found out in chapter 5 is here's this distribution of all these sample means. And yes, most of them are in here and they are close to the population mean, but there are some samples that are out here in the tails. And so it's very possible that this X bar is a significant away from the actual population mean. So if I said, here's my X bar value, what are the chances that this X bar is equal to that population mean? What are the chances? You'd probably say low probability. Because you're just, it's 1 point. This is what we call a point estimate. So it's a 1 point estimate for the population mean. And, it's a good estimate, but it's not, the probability is low that it's equal. So what do we do about that? Well, instead of using a point, what we do is we create an interval. So if we have, let's say we have a number line and here's our X bar value. We say, instead of just using that 1 point, let's go a little bit to the left and right and create a range of numbers and say, well, what about this? Now, what is the probability that that range of numbers includes the population mean? Now we could say that there's a higher probability that that range of numbers is going to include the population mean. So it's just a way of giving an estimate for your population mean that has a higher probability of being right, okay? And that's what we're going to be doing in chapter 6 is creating these things. They're called confidence intervals, okay? And so the level of confidence is the probability. My handwriting's horrible. I'm gonna try harder. It's the probability the interval contains the population mean, assuming X bar and the interval are repeatedly taken. Okay, so let's talk about what this level of confidence means. Remember when we were doing the central limit theorem, we were saying, hey, this sample right here is one such sample. We call it X bar 1, but there are a lot of different samples, X bar 2, we could take X bar 3, right? We could take all of these samples in this population. And with each of those samples, we calculate an interval around them, a confidence interval around them. And so the width of that confidence interval tells us what the probability is that that interval contains the population mean. Now I've got a simulator I want to show you that kind of gives an illustration of it. Okay, so let's go over here. This is a simulator of confidence intervals. I've set this so that the population mean is 10, standard deviation is 1, and a sample size of 5. You can set that for whatever, but what I want to show you is if I pick one sample, calculate one X bar and create one confidence interval, The number of intervals I want to map here is 1. Okay. What this does is it shows me where that is. Now, this bar down the middle is my population mean, right? My X bar is that dot on the green line. So that's the mean of my sample. And that green line is my sample interval, my confidence interval. Now, look, do you see that the 10 is contained in that interval? It's green because, look, I set that interval, and yes, the population mean is in that. Okay, now let's do it again. I'm going to calculate a different sample, and this computer program is simulating doing all the math, okay, for you. So I'm going to hit sample again, and it's going to create another interval right there. So this interval, now see how that sample mean, the X bar is that black dot, it got closer to the population mean, right? It's not exact, but it's a lot closer than the other one because it's a different random sample and there's an interval on it. And yes, indeed, the population mean is in that interval. Let's do another one. Now look at the black dot. It's farther away. So that mean is a little bit off, but again, the interval includes it. So how often does that black dot hit the population mean exactly? That point estimate is rarely exactly on, but the interval itself is often on. Okay, now let's up this from the number of intervals to, like, say 25. So we can kind of see more. So there's just 25 samples all at once. Do you see how they're moving around? They're moving around because each sample has a different sample mean. And so that moves the interval right or left, depending on where your sample mean is, because we're going a certain amount on the left, a certain amount on the right, and they're moving all around. But look, all of those sample means contain the population mean, or sorry, all of those confidence intervals contain the population mean. Now let's regenerate another 25 and let's look at that. Now look at this one. See that there are some that are red? Those are like those values in the tails. Remember, we can take a sample and we could have an abnormal sample. So say, for example, I want to know what's the average height of a college student at my college. Well, it's possible that I randomly select a lot of people from the basketball team. It's not probable, but it's possible. So in that sample, if that happens, that sample mean is unusually high for people's height. And so that actually may be far enough away from the population mean that confidence interval does not contain the population mean. And that's what is happening with those red bars. So there's a few of those that are off. Now I do it again, and look, now only one's off at the bottom, but most of them are on. Okay. Now let's jump this up to 100. Let's do 100 intervals. Okay, what I want you to see here is how many red bars you have. You have 1, 2, 3, 4. So of these 100, 4 of them did not contain the population mean. That is what the confidence level measures. So do you see here in the middle on the left, it says confidence level is 95%. What that means is if you take 100 of these random samples, calculate the sample mean, roughly 5 will not contain the mean, and 95 of them will contain the population mean. And that's what you're seeing here. Now, are there exactly 5? No, because it's never exactly how the math predicts, but it's close. There's 4 of them there instead of 5. Okay, let's randomly generate another 100 of these. Okay, here's 100. Now this one looks a little high. We've got 1, 2, 3, 4, 5, 6, 7, 8 of them that don't contain the mean. So the first one was a little under, second one's a little over. Okay, however, how many don't contain the population mean? We do it again. Okay, this time there's 4. We do it again. This time there's 1, 2, 3, 4, 5, 6, 7. But the idea is the more of these you generate, the closer and closer it gets to exactly 95% of these sample means, creating an interval that contains the population mean. And that's the idea of a confidence interval. That's kind of cool, just in case you were wondering. Okay, so what are we doing and how do we do it? Well, the confidence level is a percentage, okay? It's a probability, the probability that an interval contains the mean. So in 5, I think it was 5.3, we did these problems where I gave you a percentage. Let's use 90%. Like, let's say we want to be 90% confident. Okay, so that means that I want the middle 90% of these intervals to contain the population mean. So that means I'm okay with 5% error on either side. Now, this is a standard normal curve. So there's a z-score, we call it a z-critical, associated with these divider markers, right, that mark my 90% confidence interval. And if you do your math with the 5-3 technique, you do inverse norm, or if you're a class calc person, it's inverse distribution dot CDF or whatever that was, the dot norm CDF, and you enter your percentages, you can get a Z critical score here. It turns out for this one, it's negative 1.645 and 1.645. You can do that if you want. Remember, the inverse norm always measures from the left. So you'll be entering 0.05 for your area because that's the left-hand area here up to your divider marker. And because this is symmetric, they're both the same number on either side. You just have to calculate the one. Now, you won't really have to do that a lot in this section. I just want you to understand like how this is connecting to previous sections. And what happens is we can calculate, let's draw a picture again. Here's our X bar. This is our sample mean. We pull a sample, we find our mean, and we want to create this interval, right? Well, this distance right here, we call E, that's our error. And that distance is standard based on what your confidence percentage is, what percent you want, what this percent is right here. And you may want it high, you may not care, you may want it low, and that is going to affect what E is. Now, E has a specific formula. It's related to the Z critical value. It's the Z critical times sigma over the square root of n. You do not need to write this formula down. You will not need to use it. I'm going to show you how to do this on your calculator. I just want to show you kind of a little bit of the inner workings of how we're calculating this before we go pushing buttons on the calculator. But the idea is you take your sample mean, you calculate this error number, and then you're going to either add that much and then subtract that much off your sample mean, and that's your interval. Okay. All right, so how do we do this on the calculator? Let's pull up a homework problem right here. This is what they'll look like. So this problem is asking, in 36 randomly selected seawater samples, so we're taking a sample, okay? There's going to be 36 elements in it. So that means my N is going to be 36. The mean sodium chloride concentration is 23 cubic centimeters. So that's my mean for my sample. So that's my X bar is 23. All right. So I want to know this thing about this population of seawater samples. Seawater. So I'm going to take 36 samples and I'm going to find the average for that sample. So in picture form, here's my population, all the seawater. I'm taking this one sample here, X bar 1. Okay, there could be many samples and many X bars, but this is my one. And then I'm going to figure out, I want to know what is, construct a 90% confidence interval. Okay, so my C value, which is what our confidence percentage is going to be 0.90. That's this number here. Okay, and it also says assume the population standard deviation is 6.7. So sigma is 6.7. So these problems will always give you these values. They have to be given, your N, X bar, C, and sigma. All right, if you're on class calc, we're going to go, I'm not going to remember these numbers, so I'll hop back. You are going to go under stat here. And then you're going to go to tests. So new menu option. And in tests down here, this is called a Z interval. That's what you're going to choose. And it tells you what to enter here, sigma, X bar, N, and C level. All right, so sigma and X bar, that's going to be 6.7 and 23. 6.7, 23. And then I want N and C level. So that's going to be, N is 36, C is 0.9. Remember, percentages always as decimals, okay? And what you'll see here, right here, is that is your confidence interval. This means that a confidence interval for the population mean, because remember, that's what we're trying to estimate. That's why it says mu and not X bar, is between 21.16 and 24.83. So what the calculator is doing is it's calculating this, wrong direction, this formula right here for you. It's taking that 90% that you dictated, it's calculating it as 1.645 value, and then plugging it in with sigma and N into this formula. And then it's adding that number and subtracting that number from X bar. That's how we're getting that interval number. So what I would say is my confidence interval is 21.16 to 24.84. On the TI, you're also going to be in a new interval. So you're going to go in here to stat. And when you hit stat, you get a list. It says edit, calc, and tests over the top. And you're going to select tests. And you are going to go down to, on my calculator, it's option number 7 down here. It's called Z interval. All right, so you select that and a screen will pop up. This, and it says, sigma, X bar, N, and C level. So you're going to enter your data 6.7, 23, 36, and 0.9 and hit calculate. And then it's going to give you your interval. And it'll give you it in a parenthesis. Now, the thing the TI doesn't do that class calc does is it gives you that interval on the TI, but you actually have to calculate the error yourself. On the class calc, below your interval, it'll say ME, that's your error value. So it gives you that value automatically. On a TI, you have to do the subtraction yourself. Okay, let me write this on a number line here. So my X bar, that's my sample mean, is 23. And then down here is 21.16, and up here is 24.84. See how those are in order? The X bars in the middle, 21 to 24 is my interval. And the way that you can calculate your error, some of the problems follow up after they say calculate the confidence interval. They say, what's the error? What is E? And what that means is, what is this distance right here? Or this distance right here? They're the same. It doesn't matter how you do it. You just one of those two distances. And so all you do simply is take one of these numbers and subtract it from the other. So I'm going to take 24.84 and subtract it from 23. And that's going to be my margin of error. So I get, that's just going to be 1.84. Okay. So that's how you calculate your margin of error. You don't have to go back up to that formula and crank all those numbers out. All you have to do is subtract your mean and your endpoint. All right, now what happens when I up the confidence interval? So what I'm saying is, I'm 90% sure that if you pulled 100 samples, I would say that roughly 90 of them will contain the population mean and 10 won't. That's what this is saying. Okay. So picture wise, you're saying, hey, if we pull these 100 samples, remember the simulator? If we had 100 of those lines, you would roughly see 10 red and 90 green on average. Okay. That's what that's saying. Now, what if I want a higher confidence that my interval contains the mean? So second part of this problem says, let's construct a 95% confidence interval. So if I want a 95% confidence interval, that means that if I pull 100 samples, I want 95 of them to be green and only 5 of them to be red. So I want to be more sure that my interval is going to contain the mean. Well, what happens? In order to illustrate that, let me talk to you about if you've ever been to a fair, okay? If you've ever played this game where they have these little rings and they've got a bunch of bottles lined up and you toss the rings onto the bottles, okay? And you win a prize if the ring gets over a bottle top. I don't know if you've ever seen that, but that's like one of the games that I remember from my childhood. Well, why does nobody win that game? It's because the ring is almost exactly the same size as the bottle. So you have to hit it exactly on the nose to get it over the bottle, right? So imagine, if you will, you have a ring, you're tossing it over the bottle, and the bottle mouth is about this big, and the ring is just slightly bigger. You have very little margin of error. The chances are low that you're going to win this game. Now, what if the bottle mouth is like, the bottles are lined up like this, and you're going to throw a ring around it, but now imagine that the ring is this big. What are the chances you're going to get that ring over a bottle mouth? Now the probability is high, correct? Okay, so the bigger the ring, the more likely you are to capture the bottle. Okay, in this example, the bottle mouth is the population mean, and the purple ring is the confidence interval. So the bigger the confidence interval, the more likely I am to capture the population mean. So what's going to happen when I ask you for a 95% confidence interval? The interval is going to get bigger, because then it's covering more territory and it's more likely to contain the mean. Okay, so let's just see what happens. Let's go back to our calculator. We've got the same sigma x bar n, but now we want to change our confidence level to 0.95. Now look at it. Now it's going from 20.8 to 25.2. 20.8, that's here, to 25.2. See that? So the confidence interval is bigger, and so it's more likely that that mean is in there. Okay, now, when do you use what and why do we care and all that stuff? All right, let's say I'm testing a pharmaceutical drug and I want to know, I don't know, maybe it's bringing blood pressure down or something, and I want to know the average decrease in blood pressure. Well, in that scenario, I'm testing something, a pharmaceutical that a person's going to take. I do not want a huge, I do not want a large margin of error. I want to make sure that my test is simulating what's actually happening in the population. So in that scenario, I want to be like 95, I would say like 99% confident, because the error means somebody's health is at risk, right? So I don't want any of those red lines. I don't want to take a sample and be off in the tail somewhere and not know it. I want to take a sample and be very, very confident that the population mean is in that range. So that's an example of when that confidence level matters. Now, if I'm taking a political survey and saying, how do you feel about the president? What's the average presidential rating? That's not really a matter of life and death. So in that situation, I could narrow my confidence interval, say I only want an 80% confidence interval, and be okay. Like nobody's health is at risk. It's like, well, if we're wrong or off by a little, it's not a big deal. Okay. So that's when and why it cares. The issue though, is if you get your interval too big, then it doesn't mean anything. Okay. So let me give you an example. Wow, that's calculus and you don't want that. Okay, hold on. So let me give you an example. What if I'm measuring the mean height of a college student? I could give you a confidence interval and say I am 100% confident that the population mean is in this interval from 0 to 10 feet tall. Would you agree? The population mean, whatever the mean is of your college height wise, is somewhere between 0 and 10. I think you'd agree, right? But it doesn't help you because the interval's too big. I mean, obviously, it's somewhere between 0 and 10 feet. What I want is an interval that's small enough to help me understand something about the population without being having too much error in possibly being off. So it's this game of like, how small can you get before you get too much error going on? And so you want to pick as high of a confidence interval as possible without getting your interval too very, very big. Okay. The last thing that we're going to do in this section is we are going to calculate minimum sample size. Sometimes you want to increase the preciseness of your interval. Okay, so like we were saying, too big, it doesn't mean anything, too small, too much error. So one way to increase the precision of your interval estimate is to increase your sample size. That always matters in statistics, and that always makes things better when you pull a bigger sample. So sometimes you know what you want your margin of error to be, but you don't know, you want to know before you do the experiment, hey, how big of a sample do I have to pull to construct this certain confidence interval? And so that can be done with a formula. The formula for the minimum sample size is n equals z critical times sigma divided by the error, and that whole quantity is squared. So if you know what you want your error to be, you know your confidence percentage, then you can calculate how big of a sample you want to pull in order to create the results that you're looking for. Okay, so let's do an example right here. A tennis ball manufacturer wants to estimate the mean circumference of tennis balls within 0.05 inches. So they already know what their error can be. When does this happen? Well, like with the FDA and these governing bodies that say, hey, you're only allowed this much error, or if you're producing a pharmaceutical, there are boundaries on how much error you can have within your medication or the foods that you're producing, et cetera. So sometimes going into the situation, you know how much error you're allowed, and then you want to pull a sample and make sure that you have going on what you think you're going on. And so this is how you calculate how big of a sample you need to be the most accurate. So I want to be within 0.05 inches. So that's going to be my error value down here. Now, sometimes the error is a percentage. Sometimes it's a decimal. It doesn't matter. You can put whatever you want down there, whatever it gives you. Remember, if it gives you a percentage, like the error can only be 2%, you're going to do 0.02. No percentages in calculations convert to a decimal. Okay. Determine the minimum sample size required to construct a 99% confidence interval. Now, this goes back to where I said you don't have to use this very often, but you do have to use it here. That Z critical, that's this value, remember, on this normal distribution. I want a 99% confidence interval. That means that I have 0.5% on either side. And I want to know, this is my Z critical value, and you need to find that. So this is your, you're going to go norm, CDF. I'll do this on class calc. This is a review of 5.3. Hopefully you remember that. It's a standard normal curve. So our mean is going to be 0 and our standard deviation is going to be 1. And an inverse CDF always measures from the left. So we're going to enter this percentage. 0.5% is 0.005 as a decimal. So let's go over there and take a look. You're going to go stat, distribution plot. You're doing a normal distribution. Your mean is 0. Your standard deviation is 1. And then you are going to go back into stat, and you're going to go back into distribution and do this dot inverse CDF, and your area is going to be 0.005. This is your Z critical score. Okay, negative 2.58, we'll call it. Negative 2.58. Okay, on the TI, you're going into your second distribution function. And you're going down to the third entry, which is inverse norm. And when you select that, you're going to enter your area of 0.005. Your mean is going to be 0, standard deviation is 1, and that's going to kick out your Z score for you. Okay, so same thing there. That's going to be your Z critical, 2.58. Now it doesn't matter if you use the negative Z critical or the positive one, because ultimately we're going to end up squaring this value, which makes that negative irrelevant. So I always just put the positive in there. Okay, and then my sigma is my population standard deviation, which is 0.10. Okay, and then I crank that out. So I'm going to go, I just do my inside stuff first, 2.58 times 0.10, and then I divide it by 0.05, and then I square that answer. So this gives me 26.626. Okay. Now let's think about what this means. We are finding a minimum sample size, the minimum number of people I need to survey to have this much area and this much of a confidence interval. I cannot survey 0.62 of a person. Okay, this is how many people I have to survey or sample. So this always has to round up to 27, because if I round down to 26, it's too low. The minimum is 26.6. So I always have to round up on this value and make that 27. And that will always be true for these problems. All right, we'll do some more problems in class. Good luck, and I will see you tomorrow.